Okay, we are going to look at strong and weak acids. So you would have done a Bronsted-Lowry definition of a strong acid, and you would have learned that it was a good proton donor. If you look at what that actually looks like now in terms of dissociation, a strong acid is effectively almost fully dissociated into H pluses and A minuses, which means that the equilibrium is almost all the way to the right. It's even shown sometimes with just a full arrow rather than the two arrows that we're used to show equilibrium. Then a weak acid is a poor proton donor, and it doesn't fully dissociate in water. And that could be shown with your HA going to HA, H pluses and A minuses. And you can see there you're showing your two half arrows to show that it's an equilibrium. And it doesn't go that far probably over to the H plus and the A minus. The extent to which an acid dissociates then is used to indicate the strength of the acid, and it's represented by what's called an acid dissociation constant, which is Ka. Now, we already know that formula from when we were doing equilibrium. Your Ka is equal to the H plus concentration by the A minus concentration over the concentration of HA. And if you have a large Ka, that means that the equilibrium is going a nice bit over to the right, which means you're getting a lot of dissociation. And if you're getting a lot of dissociation, that means that you have a strong acid, as distinct from one that has a lower value of Ka. A lower Ka would indicate a weak acid. The larger the Ka, the stronger the acid. The smaller the Ka, the weaker the acid. Great. So in terms of bases then, you will have learned that a strong base is a good proton acceptor if you go back to your definitions in the first chapter on acids and bases. There's just an example of sodium hydroxide, and the reaction goes completely from left to right. So there's full dissociation there. A weak base then is a poor proton acceptor, and an example of that might be your ammonia, which dissociates only slightly and doesn't have a great tendency to go to the right-hand side of that equilibrium. So that reaction does not go to completion. The equilibrium lies mainly towards the left-hand side. The extent to which a base dissociates is used to indicate the strength of the base and is represented by the base dissociation constant. So it's another K, in this case Kb. And again, we can write out the equation for that based on our knowledge of equilibrium. So Kb is equal to the B plus concentration by the OH minus concentration over the BOH concentration. So in this case, the larger the Kb, the stronger the base, and the smaller the Kb, the weaker the base. Now that brings us on to the idea of relative strengths of acids and bases then. A strong acid will always have a weak conjugate base. For instance, hydrochloric acid there is a strong acid. It's a good proton donor. And what does that mean? It means that its conjugate base there, and if you remember, a conjugate base differs from its acid by just one H plus. So if you go over to the other side, it's the Cl minus is the conjugate base of your hydrochloric acid. It's your HCl less one H plus. But it's always a weak conjugate base, i.e. a poor proton acceptor. And of course, the converse is also true. If you have a weak acid, like your ethanoic acid, it would have a strong conjugate base. And here's an example, exactly the one I was talking about. If you have your ethanoic acid there on the left and it's a weak acid, it's not going to be great at donating protons. So it's a weak proton donor, and its conjugate acid, which is over on the other side, your CH3COO minus, which is the same as your ethanoic acid, except it is less H plus. It's the conjugate base. It is a good proton acceptor. What does this effectively mean? It means that the equilibrium for that one lies mainly to the left, which means your Ka is quite a low value. And the opposite is true for bases. The stronger the acid, the weaker its conjugate base. The weaker the acid, the stronger its conjugate base. Now, There's one extra bit that we need to do on the pH scale, and it's the limitations of the pH scale, which I don't think the guy went through for you on the last set of slides I gave you. Some limitations. So it doesn't actually show you, the pH scale looks at just the hydrogen ion concentration. It doesn't look at the extent of dissociation. So it doesn't tell you about the difference between a strong and a weak acid. pH depends only on the concentration of the H plus ions. A solution of pH 5 could be made from a dilute solution of a strong acid or a concentrated solution of a weak acid. Then the pH scale is only from 0 to 14, so it is ignoring possible pHs that are outside that, and there are some solutions that would have a pH of outside that 0 to 14 range. The pH scale does not work for very concentrated solutions. For instance, if you had a 10 molar HCl, it would come up with a pH of -1, which is not represented on the scale. Similarly, the pH for 1 molar sodium hydroxide is 14, but if you went to 10 molar sodium hydroxide, that would be 15, which is outside of the scale. So once the concentration exceeds 1 molar, complete dissociation does not occur. And it is limited, finally, to aqueous solutions. Of course, things can be dissolved in solvents other than water, and the pH scale just doesn't take that into account at all. So that's just a quick run through on the limitations of the pH scale. The next topic is going to be acid-base indicators, but I'm going to leave that till next week. Next thing I'm going to do for you now is work through a couple of examples that are slightly more challenging for calculating your pH of strong and weak acids and bases. We'll start with the strong ones first of all. Okay, so need to escape. And